Hi everyone, today I'm going to be explaining a concept in graph theory, finding a consistently oriented region determined by a directed closed curve. This sounds like a very complicated concept, but I'm eager to show you what exactly the concept is and why it works in very simple ways. Here's a story to better understand the concept. Once upon a time, there's a smart boy named Austin and the son of a very rich king, Sam. And in their backyard, Sam had built a path over his lush green grass, which he scrapped and rebuilt every month. Austin was very curious about this path, and so were all of Sam's neighbors. It was quite a busy path indeed. To prevent traffic jams, Sam made sure everybody was walking only one way along the path. Hence, the big arrows. He made sure that the path, when it intersected itself, crossed from one side to the other, so people wouldn't clump at that point, but spiced the path up by having the path intersect itself multiple times at some points. Finally, Sam made sure there were no dead ends. It was a crazy path indeed. So one day, Austin felt bored, and sometimes no grass and sometimes grass. He wanted to put a very artsy fountain somewhere where everyone could see it. He didn't want people to collide with each other when viewing his fountain, so he decided to put the fountain in the middle of a grass patch where all the paths directly around the grass patch were all pointed in the same direction, like this one. So, excited by his findings, he immediately went to his father to order a fountain and explained how he would place it. His father was not satisfied with what his son said. Sam questioned, "What if you can't place the fountain in such a way?" Being the smart kid Austin was, he said, "It always works. I'll show you." And that's our concept for today. To put this story in a mathematical sense, we're going to quickly list out the components of this concept. Sam's very special path could be characterized as a closed curve that is oriented in a specific direction, can pass through a single point multiple times, and when intersect itself, it passes from one side to another. Finally, we can characterize Austin's patch of grass as an empty enclosed region whose boundary is consistently oriented by the curve, meaning every portion of the region's boundary is traversed in the same direction as the curve, either clockwise or counterclockwise. Looks like Austin picked up a harder fight than he thought he did. But before we jump into our proof, I want you to pause this video and try to spot all the grass patches where Austin can put his artsy fountain in last month's crazy twisted path. Cool, here are all the patches labeled in blue X's. To start off this proof, Austin had a really keen idea. He knew the world wasn't flat, so he put the path on the earth. To help us imagine this, we'll need a balloon. Yes, a balloon. Or any round object so we can directly write on it. I highly recommend you do this along with me because you'll encounter different aha moments in this proof and will understand them better. Go ahead and draw a curve as I am showing you right now. Make sure it follows Sam's guidelines. After you finish drawing the curve, orient the curve by starting at some point on the curve, going a specific direction and keeping with that direction like shown. Here's the weirdest but most amazing part of the proof. Pick any patch and label it 5. Now, for every patch on the left of its arrow here, label it 4. And for every patch on the right of this arrow, label it 6. In general, the patch on the left of the arrow should be one less than the patch on the right of the arrow. Now label all your patches. I don't know about you, but when I was labeling the balloon, it became evident that all the labeling somehow fit together. If you didn't draw or orient the path incorrectly, none of the numbers seemed to clash. Interesting, right? But there's more. Pause this video and try to find a grass patch where Austin could put his fountain in using my balloon or your own. And see if you can observe anything about the number in that specific grass patch compared to its neighbor patches. On my balloon, here's a patch where Austin could put his fountain in. But when we look around that patch, let's call this P, out of all its neighboring patches, the numbers are all exactly one larger than the number in P. In a broader sense, we can make a claim that if all the neighboring patches of P are exactly one number higher than the number of P, or all one number lower than the number of P, then Austin is able to put a fountain in that patch. But why? If all the of the neighboring patches of P are one more greater than the number in P, or one less than the number in P, then the orientation of the patch must be entirely counterclockwise or clockwise, which means Austin can put a fountain in that patch. This is a stroke of good fortune for Austin. You see, all he needs to do is to choose a patch where, with the smallest number, to guarantee to his father that a suitable location for the fountain exists. If there are several patches that tie for the smallest number, then any one of them will do. We just proved that a patch P works if all its neighboring numbers are greater than the number of P here, meaning that the smallest numbered patch is suitable since all its neighboring numbers must be greater than P. Similarly, for the largest numbered patch, since the patch itself is the largest number, then all the patches around it have to be one less, meaning that the patch is also suitable. Seems like we're done here. It proved that Austin can guarantee at least one grass patch where he can put the fountain in a path, either in the patch with the largest number or the path with the smallest number. But wait, in this case, seems like the largest number is outside the path. That means that Austin can only guarantee one patch, which is this patch, which wasn't the outer region. But that's okay, because he only needs to prove that there is at least one patch to prove his dad wrong. Wonderful. But actually, a problem arises with our proof. What if the labeling of the balloon goes wrong, where two numbers conflict in a match? Let's say if a 5 is supposed to go next to an already numbered patch labeled 7, then our rule for labeling is broken. We can prove that there's no way that the labeling can go wrong. Well, unless you labeled it wrong yourself. Starting with our initial patch 5, let's say we can get to another patch P two ways, creating a ring. For the left side, if you subtract 1, or there's an out arrow, and if you add 1, there's an in arrow. For the right side, it's complete opposite. If there's an in arrow, you subtract 1, and if there's an out arrow, you add 1. Now, another cool property of this ring of patches is that the number of in arrows is the same as the number of out arrows. Since the curve is a closed curve and every in arrow that goes in must come out equally often. Now, using what we just learned, we can prove in general that the labeling will never go wrong. We again start with the initial patch 5 and somehow get to patch P, but we don't know anything about the intermediate patches. So let us say that A be the number of in arrows and B be the number of out arrows on the left side, and C be the number of in arrows and D be the number of out arrows on the right side. Now, since we know that the number of in arrows equals to the number of out arrows, we have A plus C is equal to B plus D. Now, somehow we're supposed to find the number in P, but remember that we know what the number is. Since every in arrow you add 1 and every out arrow you subtract 1 on the left side, and every in arrow you subtract 1 and every out arrow you add 1 on the right side. So, on the left side, every time you have an in arrow, you add 1, and every time you have an out arrow, you subtract 1. So that would be the number P. Similarly, on the left side, every in arrow you subtract 1, and every out arrow you add 1. So it would be 5 plus D minus C. Now, are these two values the same? Well, taking our first expression, we can change this to be A minus B is equal to D minus C. Now we see D minus C here and A minus B here, so that means 5 plus A minus B has to equal to 5 plus D minus C. And this concludes our proof. I want to give special thanks to Dr. Sam Vanderbilt for introducing me to this problem, and Dr. Austin Shapiro for uncovering this beautiful, beautiful proof. These two teachers are also characters of the story. Dr. Vanderbilt as Sam, the father who wanted the solution, and Dr. Shapiro as Austin, the son who came up with the solution. Cheers and thanks.